This is Lab 8, RC Circuits. This lab was designed for electrical engineering fundamentals. Objective of this lab, we are going to study behavior of a simple RC circuit. We are going to design a simple RC circuit using resistors, capacitor, breadboard, jumpers, oscilloscope, function generator, and digital multimeter. And we are going to calculate three things. Calculate the voltage charging across the capacitors with respect to the time. Calculate the voltage discharging with respect to the time. And also to give you a good understand about the time constant tau equal RC. Using these two graphs, this graph expresses the charging, the voltage charging, and the second graph expresses the discharging, the voltage discharging. This graph is the voltage charging with respect to the time, and this graph is the voltage discharging with respect to the time. The time for voltage charging not expressed in seconds, minutes, or minutes. It expressed in time constant. 1, 2, 3, 4, 5 time constants. Also, the voltage for discharging is not expressed in seconds or minutes. Also, it's expressed in 1, 2, 3, 4, 5 time constants. This equation, the first equation is for charging voltage formula, and the second equation is for discharging voltage formula. This equation is used to calculate the voltage charging across the capacitors with respect to the time. Vc means the voltage with respect to the time equal the total voltage applied across the circuit time 1 minus e raised to the power of minus t over tau, tau equal RC. And the second equation, this equation is used to calculate the voltage discharging across the circuit for the second graph. Vc, the voltage with respect to the time, equal initial voltage times E raised to the power of minus t over tau. What is RC? RC is a time constant. Tau equal RC. Tau is a symbol for time constants. It is shown here on this graph that we are going to prove it when we design a real circuit. After one time constant, the voltage across the capacitor will be 63%. After two time constant, the voltage will be 86%. After three time constants, the voltage will be across the capacitor 95%. After four time constants, the voltage across the capacitor will be 98%. And after five time constant, the voltage across the capacitor 99%. Similarly, if we look at the second graph and using the second formula for voltage discharging, when the capacitor is discharging, after one time constant, the voltage decreases to 37%. After two time constants, the voltage decreases across the capacitor to 40% of the total initial voltage. and after 3 time constant the voltage will be 5% across the capacitor, and after 4 time constants the voltage across the capacitors will be 2%, and after 5 time constants the voltage will be 1%. We can use this formula to prove this graph. This is a real circuit that we are going to design in a breadboard. We are going to use the resistor 10 kilo ohm, and we are going to use the capacitor 4.7 nanofarad. If we calculate the tau for this circuit, tau equal R times C. In this circuit, R is 10 kilo ohm times 4.7 nanofarad equal 47 microsecond. Tau for this circuit equal 47 microsecond. Tau equal one time constants. Time constants tell how long the capacitor charge or discharge. In this table, we are going to measure the voltage across the capacitor in the following time. Also, we are going to measure tau, the voltage during the first time constant, or tau. In our case, the first time constant should be equal to 1.57 volt, because tau for our circuit is 47 microsecond, and the total voltage applied across the circuit is equal to 2.5 volt. Please watch me design this RC circuit using 10 kilo ohm and 4.7 nanofarad, applying 1 kilohertz, 2.5 volt across the circuit. After we take the real measurements, completing this table, the students are going to sketch the graph for the capacitor charging and discharging voltage waveform using table 1. Also, students are going to build this circuit using the software Multisim and compare it with the physical lab to write their analysis of the circuit. Now I am going to build my RC circuit using resistor 10 kilo ohm and capacitors 4.7 nanofarad. This resistor color code is shown 10 kilo ohm, but I am going to measure it, selecting the range 20 kilo ohm. This resistor is shown 9.92 kilo ohm, so I'm going to use this resistor. Color code is 10 kilo ohm, but the measurement is 9.92 kilo ohm. So this for my RC circuit. Similarly, this capacitor is shown 4.7 nano. Farad, but the measurement might will be little bit different. So I am going to use the 220 nano range. I'm going to measure these capacitors. So measurement is shown 4.9 nanofarad. So this is a capacitor that I'm going to use it for the circuit. So I'm connecting resistors I'm connecting the resistor and capacitors in series as shown in this circuit. So I'm going to use a function generator and oscilloscope. I'm going to use the function generator to apply 2.5 volt square wave to this circuit, and 1 kilohertz frequency is 1 kilohertz and amplitude is 2.5 square wave. I'm going to use an oscilloscope to measure the charging and discharging of this RC circuit. Here it's my function generator. I'm going to connect the positive to the resistors. Resistor and capacitor are connected in series. I'm connecting the ground to the second terminal of the capacitors. So I'm going to connect the ground away here so I can take another wire between the ground and taken from the ground to the capacitor, so I can have a space when I'm measuring the output of the capacitors VC, so it enables me to have space measuring the output from across the capacitors. So here this resistors and the capacitor are connected to the same address here. The positive of the function generator is connected to this terminal of the resistor. The other terminal of the resistor join with the one side of the capacitors. Other side of the capacitor is connected to the ground. So this is a series RC circuit. Now I'm going to show you the function generator and oscilloscope that I'm going to use for this experiment. I'm going to use this function generator and oscilloscope. I'm switching on the function generator, and also I'm switching on the oscilloscope. I'm going to use channel 1 first. Channel 1 of the function generator and channel 1 of the oscilloscope. So I'm switching channel 2 of the oscilloscope. So here on the function generator, I am going to select 2.5 volt. So I'm going to select apply amplitude 1.25 VB. Waveform, I'm going to select square waveform. Frequency, I am going to select 1 kilohertz. Now I am going to connect my oscilloscope across the capacitors. So the positive terminal is connected between resistor and capacitors, and the negative terminal of the oscilloscope is connected to the ground. I am connecting channel 1 of the oscilloscope across the output of the circuit as shown here. I am taking output across the capacitors. The positive terminal connected between resistor and capacitors, and the ground is connected with the ground as shown here. So I'm going to take the output of this circuit VC during different delta of time between 5 microsecond to 900 microsecond. connection is shown on the circuit. This is for the channel 1 of the oscilloscope, and this is for channel 1. Input is taken from channel 1 of the function generator. Circuit is shown on this configuration. AC, and then on the function generator I have to switch on this button output, so to let the signal come out of the function generator. So here is my signal. Now I am setting the oscilloscope to 100 microsecond, and the voltage per division 0.5 volt. So that enabled me to see one wave, complete wave. So I'm stop the auto run of the oscilloscope. I'm activating the cursor, vertical cursor. I'm selecting the track here, track. Then I am selecting the track. Then that enables me to move cursor 1. So I want to stop cursor 1 at 0 microsecond. I'm going to measure charging of the capacitor. So I will stop this in 0 microsecond, so I can move the second cursor with respect to the first one. Now I am measuring my first time constant. It shows here 40, 44, 46, 46, showing 1.54. For 47 I have to get 1.57. If I go a little 48, it's between 47 and 46. I got 1.56. So the design is confirmed, similar like the calculation. So we can take the measurement for the rest of the table. So here we are going to measure this for the first time constant. The voltage across the capacitor is shown 63%, as confirming the formula for the first time constant should be 63%. Now when I'm designing the circuit, also it shows 63%. Now I'm going to complete the table, moving cursor 2. I'm stopping cursor 1 to 0 microsecond. Now I'm going to start measuring from 0 microsecond. For 0 microsecond, voltage will be 0 volt. 0 for 0 microsecond, VC equal 0 volt. Second measurement will be 20 microsecond. I'm going to move the cursor 2 with respect to cursor 1 that stop at 0. (20 microsecond) VC equal 820 millivolt. The second measurement, delta of time, 40 microsecond. For 40 microsecond, the VC shown 1.4 volt. The third measurement will be 60 microsecond. 60 microsecond VC is show 1.78 volt. For 80 microsecond, VC show 2.02 volt. For 100 microsecond, next we are going to measure VC when the delta of time is 100 microsecond. 100 microsecond VC across the capacitors is show 2.2 volt. Then we are going to measure when the delta of time 300 microsecond. Microsecond, the volt is show 2.52 volt. It's fully charged. Capacitor is fully charged. Then we are going to measure 500 microsecond. Also the capacitor showing fully charged 2.52. Then we are going to go for 520 microsecond. 520 microsecond, capacitor start discharging, so the voltage across the capacitor decreased to 1.72 volt. Then I'm going to measure when the delta of time is 560. 560. Show 760 millivolt. Also the capacitor now is discharging. Now I'm going to show 580. During the 580 microsecond, capacitor is VC across the capacitor is 520 millivolt. If we go more to 600 microsecond, 600 microsecond, 600 microsecond, capacitor is show 360 millivolt. If we go more, (700 microsecond), the voltage across the capacitor is 80 millivolt. Thank you so much for watching this video. Please complete this table using the measurement that I have shown to you, to use it to sketch the graph of the capacitor charging and discharging.